3, 2, 1, mark, T0.
This rocket isn't going to Mars or the moon. It's on a course for the Aurora Borealis. Auroras are one of the most dramatic natural phenomena on Earth. But behind that mesmerizing beauty is something dangerous. A force powerful enough to disrupt civilization and plunge parts of the world into darkness. Auroras are fingerprints of the powerful electrical and magnetic activity swirling around our planet. These rockets are armed with advanced scientific sensors that can help us understand and be ready for what might come.
There's your, it's starting to form, yeah.
Christina Lynch is an experimental physicist. She studies the invisible forces behind the northern lights, like an aurora detective. She's come to the frigid winter of Fairbanks, Alaska, because if you want to launch rockets straight into the aurora, this is the place to do it. During winter, the nights here can last up to 20 hours, and the darker it is, the easier it is to see the aurora.
I sort of pinch myself every day. It's like, you know, this is the dream job of most fifth graders, right? I get to launch rockets, right? That's pretty cool.
Don Hampton is a geophysicist and studies how energy from the aurora interacts with Earth's atmosphere.
So Poker Flat is near Fairbanks, Alaska. That's interior Alaska. That's underneath what we call the auroral zone. That's where the aurora happens on a very regular basis.
But these scientists can't just launch on any night they want. They have a precariously narrow window to get their rocket off the ground. The moon has to be down, the skies have to be clear, and the aurora has to be out. 3 years worth of preparation and building custom scientific instruments has come down to this one moment.
Rob, they just said hold the clock at T-minus 30.
We don't know what's going to come in the next hour, so if it goes south for 2 or 3 hours, that would build up enough energy to start producing auroras. This is what we do. We sit and watch little squiggly lines for hours and hours, hoping something happens. So.
Behind the glowing colors of the aurora is a force called solar weather. Streams of charged particles are constantly being ejected from the sun, some of them headed straight for Earth. Most are deflected by Earth's magnetosphere, an invisible field of magnetism created by swirling currents deep within Earth's molten core. For billions of years, this magnetic shield has prevented solar wind from ripping away Earth's atmosphere, and without it, complex life may never have evolved on our planet. But despite that protective force field, immense bursts of solar energy can sometimes have catastrophic consequences for our planet.
It causes large currents to flow in power grids, and it even affects the orbits of satellites.
The largest recorded solar storm, called the Carrington event, took place in 1859 when a giant coronal mass ejection erupted directly toward Earth. Electrical energy broke through Earth's protective magnetosphere, creating phantom electrical bursts through wires, even sparking fires in telegraph stations. But a similar storm today, in our highly technological world, could prove much more catastrophic.
More recently, we had the Mother's Day storm in May of 2024. Because of the impact of GPS, there were farm equipment in the Midwest that basically shut down or were doing crazy things. That had millions of dollars of impact on the agriculture business.
And a solar storm in 1989 collapsed Quebec's energy grid, plunging 6 million people into hours of darkness.
What we want to be able to understand as far as space weather is concerned is, do we know when that's happening? When should we look out for a heated atmosphere that might cause spacecraft trouble? If you want to try and predict that, you need to know the rules of what's making it.
That is precisely what they hope to learn when they fire their rockets into that narrow region where the solar wind meets Earth's thin magnetic shield. The aurora makes the invisible nature of electromagnetic space weather visible. Charged particles collide with our atmosphere, transferring energy to atmospheric gas molecules, exciting electrons, and emitting vivid light. The glowing colors reveal which atmospheric gases are being excited. and how much energy the solar particles carry as they collide with our atmosphere.
The main color you see when you see photos of the aurora is the green color. That's atomic oxygen. And then when you get that really active dynamic aurora, you'll see this sort of pink-red. That's nitrogen emission.
Earth's magnetic field is strongest on the poles. Here, the field dips downward, guiding the particles from the sun directly into the atmosphere. During big solar storms, Earth's magnetic field gets squeezed, and the aurora can be pushed farther south to places that normally never see it.
Look at our sky last night. The northern lights were visible in North Texas.
The northern lights seen from northern California. Isn't that beautiful?
The northern lights there could be seen in the night sky as far south as Arizona, Texas, even Florida.
Studying the aurora from the ground isn't enough. To understand what's really happening, scientists have to fly straight through it.
CM, this is PI.
Go for Sam.
Solar wind-wise, there's a pretty little quiet arc very north of us. You can see it on the Tulik camera. So everything is setting up nicely for something to happen.
Their rockets can blast up to 300 kilometers above Earth's surface. The instruments inside measure particles, electromagnetic currents, and the structure of the Earth's uppermost atmospheric layers.
As the rocket flies overhead, it's sending out this transmission, doing what's called tomography. And so the idea is that we know how much of the ionosphere is between the rocket and that receiver to give us a measure of the density of the ionosphere in that space.
That data is used to build a computer-based model.
It's measuring the physics in the space up there. And so what we do is we say, can we simulate that in our physics-based model and get the same thing that we see?
If those models match what we see in the actual auroras, it's a sign that we're closer to understanding the violent geophysics of this atmospheric light show. It takes years to create a rocket that can survive a launch, reach the upper atmosphere, and transmit enough data back to the scientists before it falls back to Earth. The NICE mission began 3 years ago, and it's almost over.
Go pull for launch. Rick?
Go.
Programmer.
Go.
Surveillance?
Go.
PLC-1.
Go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, mark, T0.
People have been trying to understand the aurora for as long as they've seen it in the night sky. The Vikings celebrated the lights, believing they were earthly manifestations of their gods. Some Inuit communities believe the aurora borealis represented the dancing spirits of animals. And as far back as 34 AD, Tiberius Caesar reportedly sent Roman troops to Ostia, Italy, convinced the city was on fire. But the city wasn't burning. The night sky above it was bathed in auroral light.
One of the first things that you can see from another planet is visible things like the aurora. And if you understand how to read it, then you can interpret more about the environment of that planet. I feel like looking around at the observable world around you and trying to understand how it works as a system is a valuable contribution in and of itself.
The aurora reminds us that our universe is full of invisible forces that we don't yet fully understand. But in the glare of a rocket, through a frigid winter sky, we might uncover those secrets. Because the better we understand that invisible shield around our planet, the better prepared we'll be for the storms still to come.